So this talk is on implementing and scaling large language models, and I'm Lily Su. I was most recently working for Discover Financial Services as a data science analyst, and in that position, I was replicating their underwriting and detecting patterns in fraud, as well as helping them validate input and output data with their mainframe to API microservices migration, and understanding the business use cases and the business impact in their customer acquisitions. So even though I have had a certain amount of time as that traditional sort of tech kind of career, let's see, let me make sure I can move my slides. I think it's this way. Okay. Okay. There was a time in my life, in the 2015 time, when I was around 25, when I was really, really struggling. At that time, I was a 3D modeler. I had made some of the green globs that you've seen on the Nickelodeon logo. I've created some state-of-the-art surgical devices. I worked on projects for Disney, Nike, Walmart, and a lot of other large name companies. I made metal designs that made it into the W Hotel, into certain hotels in New York City. And even at that time, I really struggled in my career in terms of acquiring projects, freelance projects and saying. But at that time when I was struggling and I was about $2,000 in debt, I discovered that, hey, I could use the Google search term regex to search site-wide on Craigslist for jobs all throughout the US instead of just searching and knowing people locally. So that has become that moment in my life was what caused me to become more optimistic on the power of technology, because I really felt it back then. So fast forward to a few years later, and I was equipped with the tools I needed to build applications. And I came across another, I would say, realization in my life. There's a myth out there that where they say if you build it, they will come. And we have a tendency to believe that if you build it, they will really come. And I had built, in about 2019, 2020, I built this natural language processing NLP application. And what it did was that it aggregated reviews on Yelp, and by extracting the reviews and also the customer star ratings, it could generate a top key phrases for you. For example, half-price beer Fridays, customer service as one of the low points, and it was able to aggregate this data. How it was done was that we used the Yelp dataset, which was readily available through a competition, as well as we used what was known as Luminati at the time, this proxy service that auto-rotated between 20,000 shared data center IPs, and we aggregated about 1,000 cafes and restaurants in the Phoenix, Arizona area as our pilot location, as well as scraping from other locations. And what it did was that I used the Python library scattertext and TextRank. Scattertext for calculating word frequency for the high and low ratings, and TextRank to generate a graph-based keyword extraction. And we found the word occurrences of the keywords over time. So you could compare the trend month to month to month on how, at the time, there was only regular milk, and I believe it was first almond milk that came out. But I wanted to see if we can track oat milk and maybe cashew milk, and that was something that we were able to do. So we built this application, me and a team of my friends, And we built the thing. It worked. It was deployed on Elastic Beanstalk. We had a React front end, and nobody came. So that is, in part, the motivation of my talk. Another project I had, it was around 2018. It was an augmented reality-based product viewer. And as long as you scan the QR code, which you can see on the bottom, on your phone or any device, and enable and allow camera, then you can navigate around the QR code to see new products. And I was working for a mannequin company at the time that worked with all the major apparel brands. But never took off because in 2018, it was still not COVID yet, and people on Android could not figure out how to use QR codes. So that was another situation where it was built, but nobody came. So that brings me to my talk here. I just want to talk about how when we think about the 7 wonders of the world, when we think about human achievement, a lot of the times those projects could only happen with a great amount of people. There's something amazing when a large amount of people can get together to achieve and focus on one thing over a long course of time. And I think that's something that we really care about as developers with open source. One of the key ideas of it is just this idea that if we can allow anybody to access the project, that there could be greater things that can happen from more minds put together. And even if you hate people or big cities, you can't tell me I'm wrong to say that there is still this idealization. When we hear about stories of, in Lord of the Rings, Rivendell, or Metropolis from the Superman series, or in our fantasy worlds, we think about these larger cities as greater ideals, as utopias. And as humanity as a whole, we want to be part of something greater, be part of some kind of community that is ingrained within all of us. So with that in mind, my talk is on large language models, but it has a focus towards larger organizations, building companies at scale, future-proofing the project so that there's a possibility. At least you can think about what it would take to create the infrastructure needed to build something greater with those large language models. So let's also think about humanity as a symbol and what's happening with large language models in terms of the leverage that we're getting from it. I would say that it's almost like you wake up the next day and suddenly you have 1,000 arms that you just grew. And not only that, everybody all over the world has access to 1,000 arms. So what does that mean in a company, in an organizational structure? And everybody in that organization also has the capability of generating those 1,000 arms. What does that mean in terms of the changes that will need to happen, the communication that will need to happen, in order for those arms not to necessarily be tangled up and for people to be hurt? I really enjoyed reading a book called Working with AI. Let's see, is it here? Yeah. So I really enjoyed reading this book that is related to how organizations adapt to change within AI. And I just want to share some tidbits and takeaways that I got from this book. One part that I'll quote is that they say, any company interested in moving ahead with new AI-enabled ways of doing work should begin by identifying, understanding, and engaging the complex ecosystem of stakeholders and participants in the solution. New AI technologies aren't just systems, but collections of new technology, new business models, new work designs, new skills, and new financial arrangements. And a lot of times, this is the orchestration of product managers, because this is a change management problem. And companies would be wise to establish roles that orchestrate and effectively harness AI-enabled ways of work. And these roles would include technology capabilities, really understanding the business, change management skills, the ability to build trust, and highly effective communication skills. Fundamentally, whatever the AI technology is, it doesn't prevent you to escape from really understanding what is your company's definition of success. What are the business models that are already in place in our company that work? And what's that cost-benefit trade-off for adapting new technologies to further leverage the core of what those business models can drive in terms of success for your business? So when people talk about AI, it's not necessarily just about that, and that's something this book helped me understand. That proportional to AI being used to support and automate an ever-expanding range of workforce tasks, there's just the same amount of proportion for not just creating the thing by your developers, but there's also proportionally the need to plan. And yes, you need to create and deploy, and don't forget monitor, but there takes a lot of work to continually improve these systems. And these tasks really will take time. And as an individual, it's really important for us to distinguish ourselves, both in our technological capabilities and our ability to apply the technical to the business. Because soon, everyone will be expected to have a certain amount of technical chops. It's not necessarily whether or not there's going to be a business IT hybrid role. It's a matter of the fact that every role is going to be pretty much a business IT hybrid role. It's just what type of hybrid, to what degree. So I want to talk about some of the business use cases that the book identified on platforms that are in use today. They have to deal with these aspects, which are, for example, analytics exploration, transactional sort of automated decision-making, such as your top 10 diseases. These are the top 10 recommendations for making decisions X, Y, and Z. So from my point of view, it's fairly obvious to me that LLMs can be used for chat, for referencing documents, and for speeding up development. What I can say based on the things that I just talked about was that when I was at T-Mobile in 2021 and part of 2022, I was in the procurement organization, and we were developing internal company tools that helped the big spenders, the people who were negotiating contracts in the millions and billions over the next course of 1 to 5 years or even longer, helping them create tools to better save the company money, because negotiating just a little bit of that contract can save millions. So we had built this chat-based, well, it was like a Google search, but you would type through natural language understanding the business question you would have, and this would be used by the procurement business people who are non-technical. They would type in what it is that they would need, and we generate for them results based on the tools that we built. But what the organization realized is that it wasn't very effective, because we had already trained these procurement executives to use very specific tools that were extremely targeted towards what it was they needed. If they needed to look at how they spent by by a particular organization within a particular sector on particular time periods, and they only wanted to like maybe 2 or 3 levels of hierarchy, they could get that data from a custom Excel Excel OLAP like application that we built for them. If they needed to see supply chain data, we had that in another application. Every single specific thing that they needed, we had already built a custom solution. So that's why chat wasn't necessarily enough. So in this talk, what I am going to actually focus on slightly more with everything that I'm going to talk about is more on the referencing documents side. Because what I know is that every company has a lot of unstructured data, and that data can be leveraged. And there's a reason why the companies are keeping that data, and it's because it's useful in some way. I'm talking about logging, past transaction data, all sorts of data that the company might not be leveraging, but could be insightful in terms of being beneficial to business. So since we're in a developer-focused space today, I want to share a few links with you. So these, the first one is just a great resource for learning transformers that was developed by I believe the Financial Times. And then the next 3 QR codes, and the bit.ly links are kind of hard to see, but they're Colab notebooks that you could run. There's a LangChain demo. The API keys no longer work for that, but you can see the outputs, but you could put your own API keys. There's embeddings Colab notebook, so then you could look at how to visualize words across a graphical space. And then there's like a transformer, building a transformer from scratch example that's based off of it's largely from the hands-on machine learning book by Aurelian Guerin. So I just want to take us back a little bit for a little bit of a review here of embeddings. For the people who might have taken Calculus 3, I just want to do a quick review. So we have a matrix right here in red, and the columns of each matrix you can see as I, J, and K. I is right here, J is this axis, and K is the blue one. And you can see that I being 1, 0, 0, let's look at 1, 0, which is y-axis, and then the green is 0. Max this dot, and similarly for J, 0, which is 0 on the x-axis, 1 for J, and then 0 for D, and so on and so forth. So we can start to think about word vectors as these columns right here in the matrix. Next, if you remember a little bit from physics or engineering or Calc 3 as well, that these are the basic formulas that we had to learn. That taking the dot product will give you the projection. Just like this? Okay. So the dot product would be the aqua colored blue arrow right here. The cross product will give you the orthogonal. So let's see, A and B. This would give you, it's really a 90-degree, all sides as much as you can imagine. And this is a Euclidean distance, and then there's the cosine similarity formulas. So these are the general basis in which how, when we think about embeddings, how it works. And when words are as vectors in 3D space, you can see that there are relationships that are formed. What kind of relationships, you might ask? Well, here are some examples. You can get all sorts of things such as superlatives. You could get city and state. You could get tenses. You could get plural, non-plural, singular nouns, and such. And this table you can find in the paper that Word to Rec references. I'm forgetting. So this is just like a great illustrated example of vector embeddings, how they work. So basically, you have this sentence that you're inputting, and vector embeddings is a very basic neural network. You take that sentence, and for each word, it's being compared to the words around it. And it's being compared one to the next, one to the next, one to the next for similarity. By comparing that word to the other words, we're letting the computer think of these words as numbers, just like an array of numbers. And once you have the word vectors, you'll start to be able to see that there are similarities between the words that tend to occur really closely together. So you can see how words would be compared to other words. I'm going to give a more architectural example of how actually transformers work. So transformers have the embeddings model inside of them, but they just do more. And so in the beginning, when you feed a sequence, like a sentence into a transformer, the first thing pretty much that it does is that it calculates position encoding. So I want to talk about this a little bit just because it's quite similar to the Bitcoin SEC 256K1 public cryptography protocol, in the sense that this is also a curve. It's using a function to grab some number in the other end based off a formula that graphs a curve. That curve has a particular range. For this particular example, it's just within cosine sine, so it never goes beyond 1 and doesn't ever go below -1. And if you're slightly off by a little bit, that's not okay. You're using the aggregation of plotting certain points along the sine and cosine curve in order to determine the position of a word, to save the position of a word. And so what this means is that whether your sentence is just 3 words or 50 words, we can use the same formula, and it's something that's generally easy to calculate for the computer. What you can see here is that, I'll go to the next one. Next one's a little bit better. So what's happening is that the first word is squash. So squash, you could think of that as the first column right here. So with position encodings, the odd are, I believe, sine, and the even are cosine. I might be wrong with that. But nevertheless, you have the position of the word being based on the sign being like squashed together, so that there's a greater amount, like a shorter amount of periods, and that is mapped to another sign function that has a greater amount of periods, and so on and so forth. So by extracting where that point lies on that sine curve, and so this is the first embedding, so we're here on the x-axis, but we grab the items on the positions on the y-axis. Those numbers are the numbers that we save. Well, besides the x as well, but the y-axis ones really determine the position of where that word is. As you can imagine, positions are really important. In this particular video by StatsQuest, they have an example of the squash eats pizza, where the squash was like, yum. And then the reverse would be pizza eats squash. And, squash goes, yikes. He does such really great like voiceovers for squash. But you can see that it really matters. Words are also compared to other words in this particular way. If you remember that example that I had with zeros and ones, it's pretty much a similar concept. So we can think of these columns as vectors, if you will. Or maybe in this case, you want to think about this horizontal part. They could be a vector as well. And that's how pretty much embeddings work. You're getting the similarity between the word game versus other words. And of course, it's most similar to itself, so the score is higher. So with multi-headed attention, what's happening is that instead of always comparing just start from the start of the sentence, you might start from the second word of the sentence, third word of the sentence, and so on and so forth. And it's a little bit more complicated than that, to be honest, because there is a key and value aspect to it. The key is two values, and the query is also a pair. And for each other word your word has a pair of keys, the other word has a pair of keys. And the query and the keys are mashed together in order to generate a score, and that score is then added up pretty much in the encoding aspect. And with the encoding for the transformers model, not only do you embed the words, you generate the position encoding, which I mentioned. There's self-attention, which is about saving the position of the words, including the word itself. And then there's a residual connections aspect. And then with the decoders, you're keeping track of the previous words. A pair of query values are created, and the keys of the input words are also created. And then the distances between the keys are the ones that are looked at. So with the decoder, as you can imagine, when you're training the transformers to do its job, you're not going to want it to look ahead at the next word. So that's why you could see that the kind of like the no smoking, I guess, sign in blue, and it just eventually multiplied together with other values, well, negative infinities in particular, to make them all zeroed out. And that's how the model thinks about the future words to help it learn the next word. This is what the transformer architecture looks like. Let's see if there's anything else I wanted to share about this. Okay. So as you can see with when you're looking at the word embeddings, this is, when you're training based on the decoder where it's being masked, these are the parts that are getting that are self-attending when it's during its training. So the next section I'm going to talk about is where would you actually start with large language models. And this is what I would recommend. I would recommend that you first use ChatGPT 4 just to get a basic prototype to validate whether or not your idea works, because these days, ChatGPT 4 is still the best model out there. So if it doesn't really work with that, it's not going to work as well with other models. But that being said, I mean, your project might be unique to the situation in terms of referencing data, which we'll be talking about more. So you have to take this with a little bit of grain of salt. And then there are commercial options that are available. Now, it might be surprising to you because these days Llama gets mentioned so much. But But there's a good amount of models that when they say they're open source, there are still some usage restrictions, and it's important to be quite careful about it. So with Llama, what's happening is that even though they have a Creative Commons license, they're saying beyond that if anybody uses violent language or discriminatory, then Facebook, Meta will at any point possibly step in. So what that means is that if you do use Llama, and Vicuna and Alpaca are all based on the Llama model. So what's happening is that if you're using Vicuna or Alpaca, not only do you have the Llama license, there's also additional licenses, additional restrictions that they have mentioned. So if you're using, for example, the Llama model, and your users are putting in something that Meta considers offensive or violent or discriminatory, they have the sole discretion to do whatever. Another situation, Falcon, it's also been heavily marketed as something that's very high performant. It has up to 180 billion parameters. Some of the usage restrictions say that you're not allowed to use it as a hosted service, but it's hard to understand what their definition of a hosted service might be, whether it means when you're wrapping it in an API and you're making money off the API, or you're just simply using the model and doing something that is for profit that's not directly related. It's hard to tell, so that's why just caution, to be cautious about how the licensing for these language models might be. With GPT-4All and Stable LLM, they're also marketed as open source. With copyleft, you can use it however you want, but just keep in mind that you can't keep that project proprietary. You have to open source that part and any modifications on top of that large language model. And the original owners and an entire open source community around this model will receive the rights from all the work that you've done on top of this model. So the top four here: Red Pajama, the T5 series, Dolly 2, and Pythia. These are the models that are under the Apache 2 license. So what this means is that you could use them however you want. You can keep your modifications and original file proprietary. But however, it doesn't necessarily mean that if you do something else that's a modification, and they might have intellectual property ownership to something else, that you're free from all rights and ownership obligations. You're just free to use and modify this part of the model. So that's something to just keep in mind if you're deciding on a large language model. And in terms of data fed in, data fed out, in Llama models, if your users are using that model and they're inputting language, or the output is coming out in any sense as what they determine as, they have restrictions around that particular language, then you're subject to some sort of, backlash of some sort. So that is just something to keep in mind. And the research only just means really not for commercial use. Can't monetize it. I'm going to talk a little bit now about LangChain. I think that it's a great tool to get started with large language models, just because you can swap the models in and out quite easily. However, it's a lot of people have heard about LangChain because of the fact that you can string agent tools together, and there's a good amount of sort of RAG-related concepts that you can do with it. However, it's in terms of the agent and action aspect, I would say that it's not actually very well developed yet, and it might be worthwhile after prototyping with it to develop something of your own. So LangChain is based off of 4 key aspects. Let me just go to the next slide, actually. I have a better. Just trying to find. Okay, so with LangChain, what you have is that you're able to adjust the template of the prompt. So that could be you just put in a basic prompt, or you might have some other options in terms of the formatting of it. There could be multiple prompts that you could put on there, I believe. Like, there's different structures you could use. And then there's a chat models class, which contains a large language model, and you could swap them in and out. It's almost like just like different APIs. And then you have the output. Sorry, let me see. Yeah, so with these few lines, what's happening is that you're inputting some text information that you want to reference. That's in the information part. The summary template is being fed into the summary, the prompt template area. The prompt template is pretty much the engine that kind of just like you're putting in the text, and then which includes your prompt. And you can see that my prompt has like 3 different steps. It's asking for extracting the most highly voted title based on the number of points on the information, and the information is Hacker News from October 11th, just a few days ago. So it's able to perceive and figure out the structure of the text that I input to extract the highly voted title. And then it summed all the points, and then it gave a percentage and gave me a percentage, and this is pretty much the output. So as you can see, what's great about LangChain is that you could really quickly, in a few minutes, generate something, and you can just start prototyping right from the get-go, and that's really what it's great for. So if you want to go further than that, an example then would be you create your own Python functions for the different integrations that you want. So you can think of it as like an IFTTT or a Zapier. They already support 515 plugins. I saw this week, but this is my own, like another like free API. So you're not limited to just their plugins. Any pretty much API will pretty much just work. You also have the option of document loaders, vector stores like vector databases, callback functions, and tools and toolkits. So what that means is that you can have your prompt, ask it to choose for you what are the integrations that it needs. It makes a decision, and how it makes the decision is that it thinks about your prompt in terms of reasoning, and then it creates an action, and it does that over and over and over and over again until it gets to a result. So this is what it's like known for. This is like the chain aspect. It's, like I said, a number of tools that you see. I only have 2 just to fit it in this screen. But it's a chain of tools, and it just reasons and acts, reasons and acts. I would say that this particular field, though, is not extremely well researched yet, and there's a lot of development that can be done. But if it works for you, then great. It's really dependent on the use case. So then I have an example of an output here. So for example, what might happen is that I believe that, so here my API call made a search, but my search term returned no results. So then I reasoned to kind of auto-heal by trying to search for specific terminology like the keyword that I gave it, but on Google instead. So then it generated an output for me anyway, because I believe, saw that it was going to search the API and then search for Google to append and supplement its information. So I got a result in terms of the output, but internally it was able to kind of auto sort of fix a kind of like a technical failure. So that's what might be interesting, and that's how large language models can speed development in terms of like working on some sort of projects that you're building. So actually going back a little bit more to the large language models, something I want to just point out is that the language models have a limit in terms of what you could actually input. So the token limit here has to deal with the token, so it's almost the number of words, a little bit less or more. And for a lot of these models, you're really limited to maybe around like 2,000 words, 4,000 words, except for the long T5, which has 16,000. But it's not very well used as far as I know. A lot of the models, they even just have 512 tokens that you can actually input. So what that means is that the way you can bypass it is to use vector databases. And vector databases really is just a way to, it's just a place where you can store the vector data of the word embeddings. I would recommend that because if your company already has like it's already using certain platforms such as Postgres or Elasticsearch or Cassandra, that there are already solutions that are available. And for some of these solutions, it's just additional column. It takes time for the vendor buy-in contracts to happen. So because of that, what I would recommend is to just start from what you already have. And if it really doesn't work for you, then consider the other options. In the end of the day, it's not necessarily, my understanding, that hard to store, an array of numbers. It's just about speed and scaling and compute. I could recommend some sources, such as there's a AM benchmarks that's open source that benchmark the vector database sort of metrics, but it actually widely varies depending on your use case. Summarization is going to be different from translation and so on and so forth. So I want to talk a little bit about like funny names that distributed and parallelization sort of processes have in this space. Some of them, for example, are like Deep Speed and Pipe Dream, which I think are hilarious. These are some of the notebooks that can get you started in terms of, for example, like understanding how to go about starting to use Horovod or LoRa or configuring Deep Speed. So distributed training can be divided into 3 different aspects: data parallelism, model parallelism, and pipeline parallelism. So let's see. So I'm going to first talk about Horovod, which is also the name of this traditional Russian dance. How it came to be was that Uber first, they talked about this in their paper, that they got a whole bunch of GPUs and they thought it was going to work really well. The white bars were what would be expected in terms of the speed increases. But what ended up happening was that they got the orange bars. And why did they get such a kind of lag in performance? Well, it has to deal with the network latency, because the GPUs, just distributing the workload on GPUs is not enough. You really have to, the GPUs have to talk to each other in order, in many steps. every layer of the neural network involves the GPUs gathering together and averaging some numbers out. So that's why they got this sort of kind of performance metric. And some of the solutions that are out there may be that there might be a parameter server, and that server is dedicated towards multiple nodes computing the information, and then it gets sent to the parameter server. Even if there were multiple parameter servers, the kind of communication that would need to happen is just increased so much that there's really a latency issue. So what they realized was that at the time Baidu came out with a paper, because Baidu has a good amount of background in high-performance computing, and Baidu has been had created for themselves a fork of the TensorFlow library that implements ring all reduce in C++. And how ring and reduce pretty much works is that it's kind of like telephone, where you got one person that talks to maybe two people, and those two people, they save the information, and then the other person out of the three, they are done with their work, so they talk to the other two, and so on and so forth. But it doesn't have to be 3 people, it could be anywhere above 3. And you see this kind of concept being used in Kubernetes, in Kafka, Cassandra, all sorts of distributed, that kind of like paradigms. But this is specific for how the GPU communicates with each other on a layer-by-layer basis on the data that the model is like training on. Before I go into that, let me go into a little bit more detail about this. So specifically, it's the, let's see, like I said, the GPU computes with each other to average the gradients. And then, so the gradients, the GPUs all have to like wait for each other until that gradient is like computed. Let's see. So in terms of the averaging, like with all reduce, then the nodes just make sure that they obtain like a same final results. There, like in that particular process, there is like a synchronous aggregator, and then it waits for all the gradients to be available before it computes the average gradient. Like the slower certain percentage can be ignored when the if there's GPUs that are faster. Let's see. Okay. Okay, now I'm going to talk about pipeline parallelism. So pipeline parallelism involves breaking the computation of each machine into multiple parts. Each machine runs both the forward pass and the backward pass. And then machine 1 computes the first layer on the second micro batch. Let's see. Hold on. Sorry, I had notes that I prepared for this. So with deep speed, actually, oh, sorry, it was pipe dream that I'm doing. Let's see. Right, so because, so basically pipe dream keeps all available GPUs productive by partitioning the different layers of the neural network. It also has a versioning system for the different model parameters for the backward pass. It schedules the forward and backward passes in a round-robin fashion. Oops. Okay, great. So the model is partitioning the stages, and the GPUs are assigned like certain stages. So what that means is that layer 1 and 2 might be considered one stage, layer 3 might be another stage. Each layer or multiple layers would be at one stage. And then the pipe dream is considered to operate at a runtime where the machine learning worker, which has pointers that inputs certain data. It's almost like a scheduler. So the steps that are involved are that the input creates a mini batch to forward work. The machine follows a scheduling algorithm. It's called 1F, 1B. And basically, it's when you're seeing this diagram, it's pretty much operating this like in a very low layer, like the memory level. Oh, did I just close out of that? Okay, hold on a second. Oh, okay. Yeah, that's much better. So I'm going to go into another concept a little bit. So when they manufacture a whole bunch of cars, what tends to happen is that even though every car is supposed to be the same, the engines are supposed to be the same, actually, when those cars are actually in a race, there's always going to be some cars that are faster than others. So that's really the concept of gradient accumulation, because what tends to happen is that if there are going to be slower cars, you just take the top X percentage. I kind of mentioned that a little bit in the previous slide on, I believe, data parallelism. But basically, gradient accumulation, it does a little bit more than that, but the general concept is that every once in a while, instead of at every step, the gradients would gather together, kind of like aggregating or accumulating to catch up with each other. And then it does this thing, kind of like, Friends or Sex and the City. You see only the parts when the friends get together after multiple months. And like I mentioned, the X amount of the lagging GPUs are then just not being used. And this gives a tremendous amount of speed up. And then deep speed is something that's also being used a lot recently. So what deep speed does is that it actually combines a lot of different concepts of model parallelism and pipeline parallelism. I would say kind of data parallelism as well. It's really an invention of two parts. And it's actually resting on a whole bunch of previous research, like pipe dream. You can't really have it do what it does without pipe dream. So there's the deep speed transformer, which is, like I mentioned, it's like a transformer of its own, and then there's a zero inference. So the deep speed transformer, what it does is that it's a transformer that's specific to a GPU optimized system, and it's meant to obviously minimize latency and maximize throughput. But it does that by solving the problem of how in the past, when you're computing, I mentioned before, queries and keys, those queries and keys, they rely on previous information. So there's all these data dependencies. So what it does is that like recognizing that because there's all these dependencies on previous work that has been done, that's a huge amount of like sort of latency. So it does what it's called global synchronization, which really takes all these items that have dependencies in the data, and it like creates one chunk so that all of that fits into one thread, and a new kernel is created out of that one thread. My understanding is that when a new kernel is created, it's like a difficult process. So what they do is they make sure that the batch sizes are increased, so then there's less of a bottleneck in communication. And then the transformer has all these operations. So it isolates the data based on what those, like the data is dependent on. And then the kernels themselves are also fused based on like these like element wise operations. And it's using a particular type of scheduling strategy. And then it also uses tensor slicing, but I think I'll mention that later. And then the other aspect of what DeepSeek does besides the transformer is like zero inference. Inference just means that after you train on something, it's giving you the results. Like after it's trained on something, the model can be used, so you can input things and then get you back the output that you need for new data. So with zero inference, it uses the GPU to support large batch sizes. And the large batch sizes usually are what's causing the latency of fetching the model weights. It's specific in utilizing also the GPU and an NVIDIA-specific memory store to store the model parameters. Because what they also realize is that there's certain data that you don't really need to fetch until maybe you need to fetch for the next word. So because of that, what they realize is that any particular institution that is training a large language model, they already have, like, if they have the GPU, they also have a good amount of CPU, and since it's an NVIDIA graphics card, like they also have that aspect of memory, the NVMe memory. So because of that, they're storing the extra data that they don't need right away into other aspects of the computer. And that way it limits the GPU memory so that the GPU can do its best work. And then besides that, there are other things that they do, like the gradients are quantized, which means that they're compressed in terms of their data format. And then gradients that are close to zero are set to zero. And then it kind of does kind of like a data lake kind of, what do you call it, like data differential kind of sort of function where it transmits the difference, which is the error between the original gradient and the quantized version. So it's only saving the difference instead of grabbing the actual item and then doing the subtraction and everything. It just gets the changes. So let's see. And then also uses tensor parallelism, which splits the individual parameters across the multiple GPUs. The gradients and optimizer information are divided into stages and compressed independently, and the compression is parallelized. And then it also uses a mixture of experts, where the data layout transformations are combined together into one kernel, and just by doing that, it causes, according to them, a 6-time reduction in the latency related to what they're doing there. It fixes like a gating function that's been causing latency overhead as well. Another aspect of research that's been super useful is QLoRa, which is based on LoRa. And basically, what it does is that it's really It's a compression technique that compresses the model in a way that one of the notebooks I shared allows you to run a model on a single GPU. It's a T5, and it's usually like many billions of parameters. And the fact that you could fit it onto a single GPU, that really saves a lot of costs. So what it does is that it created a new data type, which is considered the 4-bit normal float. And it's using an estimation of the input tensor instead of the actual number itself. And how it's doing is that it's statistically computing like a quantile of all the data. So that really saves a lot of space. And then when it's doing this process of compression, it's doing it twofold. So it's quantizing the quantization constants. And then it uses a particular kind of product out of NVIDIA's sort of unified memory system. So what it does is that particular NVIDIA product, it handles when the GPU gets out of memory. And this is an example of what's going on here. If you missed the notebook part and any of these concepts are of interest to you, here are the notebooks again. So now I'm going to talk a little bit about knowledge retrieval architectures. Like I mentioned earlier, a lot of companies have unstructured data, and this data could really be useful. And like I mentioned also that there's this limited context size. ChatGPT 4 has 4,096 token, like a 96 token limit. So with that, the knowledge retrieval architecture can help with that. In addition to making large language models just perform better based on specific data that it's retrieving. So Realm is really a BERT large language model, and it's just trained on Wikipedia. But what it's doing, in terms of the training process, is it's just doing filling that blank. It's in the paper, it actually talks about it as almost like copying copying homework, in terms of, because you're running a large language model, and then you're using this additional architectural concept to extract from documents to get the answer. And the results of that is that Realm that was trained on only 300 million parameters seemed to outperform T5, the 11 billion model, just using BERT, and it's 30 times smaller. But what's really what this architecture system is really used for is that when you have specific documents that you want to train, I just want to mention that. And when I say filling the blanks, what it does is that it kind of randomly masks. When it's training, it's masking certain words, and then training the model to fill in those words that it doesn't know. But also making sure that it doesn't find documents that are literally the same documents and the words exactly aligned to each other. With RAG, which I'm sure a lot of people have heard of, it's really everything that Realm does, but it's just fit to not only just the sequence, but also the token, but also sequence. So instead of just filling the blank for one word, it's able to do a question answering method so that it can generate sentences. And because they can generate sentences, they've really developed metrics in terms of how to measure the performance of the model to detect which of the top 10 sentences are better than another. So it's ranking like a talks X amount of sequences, and that's what it's pretty special about it. Besides that, I believe what they also do is they made sure that they can take multiple documents to combine multiple documents into one comprehensive answer. And what that might mean is that there might be, document 1 can come, it generates 4 words. Each word might be from a different document. They're able to do that kind of chunking. And then retro goes into more detail about that. It is really what RAG does, but then I believe it's scaled up, and then it also does the learning in an autoregressive manner, so that in the stock market, autoregressive means that when you're looking towards the future, you're extracting patterns from yesterday, a week before, a month before, a year before. So it has the same concept with retrieving documents, and it's highly performant in terms of being able to chunk the documents. And because it's autoregressive, you don't necessarily need to feed in particular documents, I believe. And then there's Atlas, which is an unsupervised learning technique. All the previous architectures were based out of BERT, but this one is based out of the T5 sequence-to-sequence architecture. So like I mentioned in this slide, it's looking at ranking it whether or not a document is useful or not. And in this way, what Atlas is also good for is that you might have a lot of documents, but the documents are not necessarily labeled in any way and still able to extract some form of meaning. So besides the knowledge retrieval architecture, that's just one technique to extract and validate truth and further information about the output that you want. There's also knowledge graphs. These are some of the aspects that knowledge graphs can be useful. You can get context awareness, helped in the recognition of people, places, organizations, and then it can capture semantic relationships. So besides just person and cat, it could be person owns, cat that owns is part of the line that's connecting the dots between person and cat, and that line might be useful for your use case. And then the structured basis for fact checking, so it can validate claims, it can ensure the accuracy of information. There's a good amount of writing out there, but this is also still an open domain of research. So I've just extracted some of the industries where this particular method could be a good use case for. I haven't done necessarily that much reading into it just yet, but as you can imagine, in any particular industry that requires some sort of information, these knowledge graphs could be possibly used for conceptual facts, rules, procedural common sense, and so on and so forth. So yeah, that's pretty much my talk. I hope that was interesting to you, and love to hear what your use case would be for the work that you're doing with large language models. So feel free to reach out and connect to me on LinkedIn. I'll share my slides with you guys if you connect with me on LinkedIn as well, and let me know how I can help you with the use case that you might have. Thank you.